So it says represent 4 times 6. 4 times 6. And the first one says set model rectangular approach. Okay. So envision an ice cube tray, and now just think of the ice cubes. So sort of like take an ice cube tray, kick it out, and there's a set model rectangular array. The one thing to remember that even some of the things in this book sometimes goes against this, but 4 times 6 means something different visually from 6 times 4, right? You want to set up a very constructed idea for a student, and then later you connect commutativity with them. Are you with me? So 4 times 6 specifically means how many rows, how many columns? How many rows? 4, good. So you would just start doing, so I want 4 rows, 6 columns, right? So you just draw a bunch of circles, or whatever your favorite shape is, really. So it's just taking, so a set would be something like this. Wow. There's a set of 6 things, correct? So set model rectangular array approach is just organize that shit, really. Less chaotic. So it's still pictures. They could be little triangles. They could be whatever pictures you want. They're just set up in an array. Okay. So that's that. And then the rest of them are just basically, so measurement model would be just like this. Huh?
Like how would you draw out a measurement model with that?
Oh, it's the tray, not the cubes.
Okay, so it'd just be like.
So it's literally, yeah. It's literally this and 4 and 6.
Okay.
And, yeah. Does that make sense? The tray versus the cubes. That's the way I kind of keep it straight. They're basically the same thing. To be really honest. Yes.
When you draw the set around for either the columns or the rows for the set model? Would there
not
be sets though?
if you were doing an actual problem where, you could, but this captures it right here.
Okay.
Yeah. You're thinking about if I had, every group had 4 members and I've got 6 groups. Then you could identify one group with 4 members and then just put 6 of those, right?
Yeah, I'm thinking, but you just arrange it
Yeah.
show.
So this is a set model without using a rectangular approach. So you have separate sets and you have 6 of them, right? And in fact, the picture on page, I think it's the very first, bottom of page 101. They show you just, I think they use coins or something, I think. So they just show you a bunch of circles in an array versus empty spots in an array. I like it. We're gonna see very soon, we're gonna see, we're gonna have kind of a silly amount of definitions coming up. And I just wanna let you know ahead of time, that's gonna happen. And they are sort of, the words are not nearly as important as the process they describe, right? Because a student, you're not gonna tell a student, for example, pretty soon I just wanna give you one example. We're gonna talk about, let me see, where's a good example? Yeah, 1 column front end estimation method. Yeah. You're more than likely not going to tell a young student, okay, memorize 1 column front end. It's going to be the process that matters. You with me? Okay, so that's in our future. It's going to be several things like that. That's going to be so exciting. Okay. Is that enough for that, Brooke, or do you have a, let's see, which one was it again? It was number 2, okay. Yeah, so Ryan, part C says, set model repeated addition approach.
Okay.
That would be
what I think of the sets is.
Totally. I love it. I agree. Yeah. Okay. So to me personally, this is kind of silly to call this a set model, but there it is. Yeah. So you just take the elements out of the little circles and just put them out in the field of wherever the hell this is, right? Here they're all protected. Here they're all like, ah. Okay, is
So
that?
C, they'd be in the circle?
Yeah, C
It'd
would
be like
be
four
this, and
circles?
you just put how many of them?
6.
6, yeah. Okay. Now, again, a lot of this is silly to us. We understand that, I don't care how you put it, it's all the same damn thing. It's all freaking 24, Jeff. Holy shit. But again, somebody who's just learning what the hell multiplication means, who only recently learned how to identify what 6 things are, I mean, they're not going to see how they're all lead to the same thing. They're not going to expect it to have to lead to the same thing. Okay. Anything else? Homework stuff. Yes.
Can you go over 3.2a, number 24, part B, the multiplicative magic square?
Oh yeah. All right. How do I give it a hint without? Okay, so the additive magic square is pretty straightforward, correct? Blah blah blah. Yeah, which is what a normal magic square is. They have to add up to be the same thing. So you can do a little trial and error. There's something very specific about the number that's got to go in the middle, and I think on that one they actually gave you what number's got to go in the middle. So if I have the numbers 1 through 9, what number is in the middle? What number is in the middle of 1 through 9? 5, right? So that should go in the middle of the square because, so think about this, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay. 1, 2, 3, 4, 1, 2, 3, 4. So 5 is in the middle, is that cool? 1 plus 9 is 10, correct? So 1 plus 5 plus 9 is 10. 2 plus 5 plus 8, I'm sorry, you can do it, Jeff, 15. 2 plus 5 plus 8 is 15. Do you guys see that? That's why it makes sense. 5 goes in the middle because it's able to make 15 the most ways. Now, that's additive magic squares. You're all like, that's great for that, Jeff. I asked about the freaking multiplicative magic square. Oh, holy shit. There's a few different answers, but they all basically come down to the same thing. Don't you wish they had said additive instead? Of course you do. When I multiply, what comes into play? What actually ends up adding when I multiply? This is such a strange question, I know. There's something I would multiply where I end up adding, and I don't just mean repeated addition. I mean straight up add. Really weird question, yes? Kick ass, thank you. Okay, I knew it was a weird question. Okay, but you saw where I was going. So if I do like x squared. The funny thing is they asked this question before we even officially talk about exponents, but okay. X squared times x to the 5th would be x to the 7th, right? Not x to the 10th. Is everybody cool with that? Okay, and we'll talk a little bit more about this later. So that's my one clue to you, is think exponents when you go to do that multiplicative magic square. Yeah. Okay. Sure. Yeah, the numbers 1 through 9 won't work. Yeah, very true. Okay. Anything else from homework stuff? Okay, I like it. By the way, I am grading old homework, and what I normally do with the old homework for like test 1, the homework that you guys turned in, some of you guys haven't gotten it back, because what I normally do is I'll grade the students who made lower grades on the test first, because they need more help from me. Does that make sense? Because, I'm only one person, so I got a big old stack of stuff to do. So one way I do it is to do those first. I am noticing some people seem to have access, well, 2 things. Everybody has access to answers to set A problems. Do you guys all realize this? They're on the back. I think, is it all the answers or just the odd? I can't remember now. All of them. It's crazy. And then there's no answers to part B, correct? Now you see why I gave you some in one, some in the other one. Because I always do that. Every time I have normal math books have like every odd problem has an answer and every even one doesn't. So I always assign stuff like every third one. So that every other problem they can actually see the answer and every other problem they can't. So you have a little bit of a safety net to check and a little bit of no safety net to get ready for a freaking test where you have no safety net, right? Does that make sense? Unfortunately, some people are just copying stuff for part A, which is not good, right? If you honestly get it wrong and you look it up and you see what the right answer is, don't just erase that shit and put the right answer. It's not good. Okay, so be really careful about that. I also think that some people have access to the actual solutions manual because there's some answers to part B stuff that's exactly word for word what's in the manual. So you can take two things away from that. The more evil lesson is if you find solutions manual, make sure to paraphrase really well so that it's not so obvious. Okay, don't take that lesson. The more important lesson, without flicking you guys off, is don't do that shit, right? It's sort of like finding your Christmas presents early. When I was a little kid, we did that once and we thought it was so cool until Christmas Day came and I'm like, I know what's in these things, damn it. So finding a solutions manual is sort of like finding your Christmas presents. It seems great until you get to the test. And then you're like, oh shit, I have no idea what I'm doing because I didn't have to do anything. Okay, I'll stop. I think most of you guys, to be honest, I love it. Some of you guys, okay. Anything else from homework before we get back into finishing up chapter 3? Okay. We did part of chapter 3, and I'll just review kind of quickly here. Do you guys remember how to kind of more formally identify when this is true or why this is true? Another way to write this, A less than B, what does that mean? Must be true. Do you guys remember? So again, why is 3 less than 5? There's a few different ways to answer that question, right? Give me one way to answer why is 3 less than 5. How would you show somebody 3 is less than 5?
You can add something with it.
All right, that's cool. Exactly. If you have to add something to one of them to make it become the other one, that's obviously the lower one, right? And then you can sort of see like a subtraction problem. Bill's got 5 trains and Sam's got 3 trains. Doesn't Sam need more? Therefore, Sam is in a situation where he has less stuff. Therefore, 3 is less than 5 in general. Are you guys with me? And do you notice what I just said? There's sort of 2 levels. There's trains. I can hold trains. I can see them. I'm Sam, and I got 3. And there's Bill with his 5. You know, I can see it. I can hold them. Versus 3 less than 5 written on a board, right? Pure math, trains, right? So I can see that. And that's the connection that students aren't gonna, you gotta kind of work them through it. The connection between what they can hold versus what's written on the paper, right? So I like what you said. So in this case, 3 plus 2 equals 5, and that's why 3 is less than 5. So how would I write this?
A plus N.
Yeah, A plus N equals B, kick ass. And we did a few other things with that. We did some transitive property. Do you guys remember the transitive property? One real life example is if I'm older than you and you're older than somebody, then I'm older than the somebody, right? And I call it the duh property, right? If some number is smaller than this number and that number is smaller than this number, then that number is smaller than that number. It kind of carries. Okay, so we kind of did some stuff with inequalities, and I used the definition, the sort of this here to kind of feel out the transitive property. And I think that's pretty much where we ended off last time. Yes, okay, I think so. How would you show a student this fact? If A is less than B, then A plus C is less than B plus C. How could you show a student this fact? What could you do? Yes?
You could replace the variables with numbers.
All right, you could do a specific example, right? To feel it out. So what this requires is a true inequality statement, and then you add stuff to both sides. That's what it requires, correct? So give me something that's true. An inequality statement that's true.
2, the symbol, and then maybe 6.
6, kick ass. Right? Then you can ask the student, pick a number and add it to both sides and see what happens. So that's the level of, that's not really a guess and check, correct? That's more like solve a simpler problem in a way. All right, so pick a value for the variables and just get a feel for it. That's nowhere near a proof, because we could have just picked 2 and 6 might be the only numbers that work. We know that's not true, but before we know it's a general truth, I don't know. That could be it. So then no matter what the student picks, if they pick 3, you end up with 5 and 9, and then you say which one's bigger, and they say 9's bigger, and you're like, holy shit, look at that. You don't say that. But the inequality is still the same. You with me? Okay. All right. How could you then start to develop a more general idea about this? How to show them more generally? Yes?
You could do it with shapes or something.
Shapes, okay, so it would still be a concrete example, but you could have something like Bill's got 2 and Sam's got 6. Sam's always got more. What's up with this kid? And if I give Bill 3 and I give Sam 3, they still have the same, Sam still has more, correct? So that's just kind of another, that's like a more concrete example of this specific math example. Yeah.
Well, if A is less than B, then no matter what you add to, okay, wait, no, if A is less than B, then no matter what you add to, if you add the same number to both of them, you're still gonna have like that same.
Yeah,
idea.
okay. So let's see. Wherever I put A on the number line, B must be to the right of it, correct? That's what this being true means. What does adding a number to a given number actually do? So if I'm sitting at 3 and I add 2, don't I move that way twice? So if I add C to both of these, aren't they each going to sort of move over by C? So you can start with getting a student to understand, if I add a number to another number, effectively making it move more steps over. And then you get them to accept that. They're like, yes, I can see that. And then you go, okay, so add the same thing to both of those. Now, of course, you're going to want to do several concrete examples first. And then you say, okay, if I add C, it just moves over by C. And if I add C to B, it just moves over by C. Which one's bigger? Still, B plus C is still bigger. Okay, maybe. What model am I using? Measurement model, kick ass, right? Okay. Measurement model is good for this, because if you try to use set model, well then you run into this weird thing where you're like, okay, I gotta have A of these. How do you represent A of these? That's hard to do you see what I'm saying? Okay. So just in case anybody was curious, there are certain situations where this works and this doesn't. Right? There are some situations where one is better than the other one, but there's some situations like this one where it just is not going to work. Okay. How we all do. And this, of course, is a fact that I know you all know. Okay, I like it. Okay. This is also, I don't know if you guys remember this, but a method for subtracting. So if I want to do 10 minus, yeah, sure. If I want to do, so 10 minus, that's not a good example. Hold on, sorry. 20 minus 11, sure. Whatever, Jeff. Okay. Yes, okay, I like it. And a student's doing this, right? Okay. So, kind of a quicker way to do this. Obviously, 11 is less than 20, correct? And there's a certain distance they're apart, right? And that distance is actually the answer to a subtraction question. Is that cool? Subtraction just really means how far apart are these things. So I've already told you this, but I don't think I showed you like this. So if I move this down by 1, I have to move this down by 1 to maintain the same distance, correct? Which is sort of what that A plus C is less than B plus C thing kind of leads to if you include subtraction. And 19 minus 10 is a much easier problem. I don't have to carry or do any of that shit. You guys see that? Maybe. So this leads to when I'm teaching like probability and a student's got to do this, right? One thing they say is, well, I got a calculator. I'm like, great, this is great. we should be able to do this. So watch. Let me see if you guys are cool with this. I would make 1 go to 0.9999. And I'll make this go to 0.6238. Does everybody see how I moved them over by just a little bit, the same amount? So of course the answer to the subtraction is the same because of the same distance apart. Do you guys see that? So then I can just do 3, 7, 6, 1. Sweet. And that leads to the ultimate shortcut. What makes this 9? 3. What makes this 9? 7. What makes this 9? 6. What makes this 10? 1. So that's how you do 1 minus any decimal. Okay. So you can go there straight from this level of stuff. You can go there, right? What's really funny is the things we're talking about now, people forget it when they get to calculus or something. And then I remind them, yeah, if you just move this shit by the same amount, it's the same distance, so the subtraction should be the same. So we're using something silly basic to help with these freakier problems. Okay, I'll stop. Okay. Boom, boom. Oh yeah, and then you got this. Now I want to talk a little bit about this. Might as well get a little ahead. A less than B. If A less than B, then what's true if I multiply both by a whole number that's, we're always talking about whole numbers right now. What happens if I multiply it by a whole number that's not 0?
So it'll be AC will be less than
It'll be the same, it just goes higher up in the number.
Yeah, so it's not this. If I already have something that's B is bigger than A, and I double A and I double B, this moves up by A, this moves up by B, right? Does that make sense? So they're not going to be the same distance apart, but the inequality is going to hold for damn sure, right? Now the bigger dude is even bigger than it used to be away from the first dude. Are you guys with me? Now, real quick, do you guys remember when you're solving something like this and you got to this point? What you had to do? Solving an inequality. Why is that not done yet? X is not by itself. There's still a negative there, of course. So what do I want to get rid of? Freaking negative, right? How do I get rid of the negative? If there was a 2 here, what would you do? Divide by 2. So what's there? There's a -1 there, right? So I'm going to divide by -1. Is that cool? Does anyone remember what happens?
Does it remain the same, just it's not?
This has to flip. You guys remember that? Anybody remember that? I love you guys. Even if you don't remember it, does that make sense yet? It does make sense? All right, if it makes sense, explain it to me. All right, real quick. What I always show my students when I talk about this, when we're doing inequality solving, which one's bigger? 2. If I multiply or divide both sides by a negative, which one's bigger? 1. What'd the sign do? Yeah, so if I multiply or divide by negative, don't I change the side of 0 it's on? So whatever was bigger is now smaller. Even if they're both in the same side of 0, when they come over here, you see how this guy is less, but now he's bigger. You guys kind of see what I'm saying? Maybe? Okay. So that's my favorite answer to any question a student has is, why does that work? Because that's the way it works. I mean, it's just the reality is what happens. Okay, enough of that. So officially in this class, we're not using negative numbers yet. Okay, but I just want to show you that real quick. Blah, 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 blah. Okay, so you guys remind me, what would that mean? What does 11x mean? 11. Make it more basic for me. Doing what? Addition, I love it. So multiplication is repeated addition, right? So this would be, Jeff, 4. You can actually see that's a little foreshadowing as to why I just changed the. I don't. Okay. So somebody in history, and the history of mathematics is really cool. Someday I'm going to make a history of mathematics class that nobody will take, but at least it will exist. But at some point in history, we had to decide where to put the 4, right? Because there was some poor fool that's like x plus x plus x. He had 80 freaking x's, and he's like, no. Isn't there just a way to communicate to people that I have 80 of these damn things, right? So we had to decide where to put the number. There's no reason it had to be there. We just decided that's where to put it. So if I see a number in front of something, that means it's that many of those things. Add it. You guys kind of with me? So then we get this guy here. And he's like, I want to make up a shortcut too. And he's like, that damn person already put a 4 in front. So he's like, I could put it there. That looks like division. I could put it there. That just looks weird. I could do this. Like, that really looks weird, right? All right. So finally, there's just like, let me just put it there, right? And again, this is something that I love the classes where I have time to put this in, this idea of the symbols we use. So you guys have already seen this shit for sure. You've seen this like a crazy amount. The symbols we use for numbers didn't have to be what they are. The meaning of where we place things didn't have to be what it is. Where we put things didn't have to be where they ended up. Do you guys see what I'm saying? So now, when a math student comes along, they just have to catch up with the decisions that were already made, right? So very quickly, I want to go through all the definitions of exponents. So basically, all the exponential properties come from that fact. It's just a quick way to write, I've got this many things. So this means I've got this many x's adding. This means I've got this many x's multiplying. Correct? Okay. I like it. So the very first property that comes off of that decision is something we just did a second ago. Something like this. Right? And of course, you get students that always say x to the 10th. And they look at me crazy when I say no, and they're like, it's times, Jeff, it's times. But nowhere in this problem, in fact, I'm going to say 2 things. Nowhere in this problem does it say 2 times 5, right? And here's something that really gets people freaked out. I don't see a 2 or a 5 in that problem anywhere. I don't see a 2 or a 5 in that problem, and you're all like, dude, something's missing. You need glasses, you need meds, you need more sleep. But what does that symbol error actually mean? I got 2 x's, and I got 5 x's. So I don't see a 2 or a 5 anywhere. So if I got 2 x's sitting next to 5 x's, obviously I've got 7 x's. So the way to show that is you got x times x, and then you got x times x times x times x times x, and then you just count, and sure enough you get 7. Okay. Kick ass. Not too bad, not too bad. So then that immediately leads to what this might mean here. If multiplying means I add how many x's I'm keeping track of, dividing obviously means I'm losing, I'm subtracting. It's a beautiful analogy, right? When I multiply, I add powers, right? That's from a million years ago. There was a whole other thing to that, but I can't remember. And to show a student this for real, x times x times x times x times x over x times x, these cancel. I got 3 left. Shortcut, 5 minus 2. Right? Okay. Not too bad. Not too shabby. All right. Does anyone remember another property of powers that we haven't talked about yet?
Are we going to talk about negative powers?
Totally. Eventually. I'm probably going to throw it in today, even though we're still dealing with just whole numbers. But to make a complete idea of exponents, I might throw that in. What about this? Yes.
Would that be 5
kick-ass. 5 groups of 2x's, right? 5 groups of 2x's, and of course that's the definition of what operation? 5 crates with 2x's in each crate. How many total x's do I have? Isn't that just the definition of multiplication, right? So then this is where you would multiply exponents. And you can do that by, what's anything to the 5th power? It's that thing multiplied by itself 5 times, correct? So it'll be x squared times x squared times x squared times x squared times x squared. And then you add up those and then you realize multiplication is a shortcut to that. Okay, 11. I know this is a huge review, but we're just going to go through real quick. Okay, I like it. What about, so here, there's a really cool little analogy with something. I'm going to do a little recall. What was this here? Yeah, right, that's distributive property. And this is really where it becomes something I have to do. Like if I put a 3 here, do I have to distribute to figure this out? No. So I could do 3 plus 2 is 5 times 2 is 10. Or I could do twice 3 is 6 plus twice 2 is 4. 6 plus 4 is still 10. So the math is like, do whatever you like, right? But if I do this, I don't have an option anymore. I can't do x plus 2. I don't know what the shit x plus 2 is, right? Some students, in some classes, I don't know, I used to teach now, shit. They would balk about the fact that we were so adamant about, please excuse my dumbass son, or whatever you want to use, PEMDAS. We were so adamant about it, and all of a sudden now I'm going, no, let's multiply first, right? And I don't blame them if they're being beat on the head about follow the order operations. Is everybody cool with why we're allowed to multiply all of a sudden instead of add? Because in the parentheses, I don't have to do in the parentheses first. Do you guys know why I'm allowed to do that? Like, just tell us, man. All right. So remind me, real quick, what's this mean? What's it really mean? The very first thing I wrote up on the board today. What's 2x mean? X plus x. So coefficients, repeated addition, it's multiplication. Exponents, repeated multiplication, right? So what is 2x plus 2's then? It would be x plus 2 plus x plus 2. What properties could I use then to get like terms together? I could use associativity and commutativity, right? Of course, we're just able to just go, how many x's are there? 2 x's plus 4. So the shortcut is just a shortcut. Distribution is just a shortcut, right? And that I always want to show my students that, especially when I'm teaching a level where they're basically learning order operations. And then I do this, and I'm like, I really want to make it clear, we're not going against order operations, we're reorganizing it so I can do it a different way. So, what does all this shit mean, Jeff? Because that's not exponents, that's what we're talking about. So if I have something like this, yeah, I can do that now. So real quick, coefficients are based on addition, correct? Because to this means that plus that. Exponents are based on, what are exponents based on? Multiplication, correct? Do you see how coefficients work well? Well, I always say it plays well. These play well together. Coefficients play well with addition and subtraction because they're based on addition. Exponents are going to play well with multiplication because they're based on multiplication. Yeah.
Okay. It's what that is 2 groups of 4 and.
I like it. So you could do this.
And then, yes.
Do you see how that's analogous to this? Right? Same idea, except now it's multiplication because it's exponents. And then I can just do 4 times 4. And then x cubed times x cubed. So then what's the shortcut we can develop? 4 squared, x cubed squared, right? Do you see how that's just another form of distribution? So that's exponential distribution, but who cares? It's just distribution. So what am I allowed to distribute? I'm allowed to distribute stuff that work well with the operation that's happening. I can distribute a coefficient across addition because coefficients are based on addition. I can distribute an exponent across multiplication because that's what they're based on. Are you guys with me? And then you get a student later that'll do this. Well, it's even worse than I wanted it to be, Jeff. Okay. What went wrong, or did anything go wrong? Does that look okay? Do you guys see what went wrong? What operation is inside? Addition. Exponents are based on multiplication, so they will not play well together. It should not be that easy. Does anyone see what happened? What's the right way to do this? If I ask you to do 13 squared, or let's do 27 squared by hand, what would you write down on your paper? 27 times 27. Okay, so now how do I do x plus 2 squared?
X plus 2 times x plus 2.
Yeah. And you remember I have to FOIL this bad boy, right? Do you see I'm going to get a middle term, right? Okay, I like it. I always like to see people's reactions. All right. Remember that? Is that all right? This is a beautiful example of what I try to show people. Why? Because to the student, this is going to make sense. This flows. We distribute shit all the time, Jeff. Why can't I just distribute that? Because that is based on multiplication and that is addition. They're not going to play well together. You guys see that? Now, depending on what level you end up teaching, you might get an opportunity to say this or you might not have to say that. But it's kind of good to introduce it wherever you can. Certain things will be easier to work with than other things based on what's going on. This is addition. Exponents not going to be easy because it's not based on addition. Okay, I like it. All right. So this is multiplicative distribution. So as long as, exponential distribution. As long as everything inside is multiplied, I can just distribute that power. I love it. Let's do something a little bit freakier. Does anyone remember what this is? All right, we got one guess is for undefined. One vote for undefined. We got a vote for one. Is that it? I got a vote for 0. Okay. All right, so how the hell would I investigate this? So let's go back. Remember this property? You're like, yes, Jeff, we knew that freaking property when we came in. Okay, great. Can you set up a similar problem that would end up with x to the 0? Yes?
X0 over x equals 0?
No. So what has to be true about the power, since I'm going to subtract them, how would I make sure it ends up with a 0?
0.
No. So for example, if this was x squared, what would have to be here so that when I subtract you get 0? 2. Everybody with me? And what is something divided by itself? So then x to the 0 is 1, right? I still get students who are in my pre-calc, my calculus, they still don't really get that. And the thing I always try to remind people is, so this is true. Start with 1, right? Now multiply by x and multiply by x. What is that so far? What is 1 times x times x? 1 times x times x.
1x squared.
X squared, right? Is that cool? X squared. Now take an x away. What's this?
X.
X. Now take an x away. 1. So this is x squared, this is x to the first, this is no x's, x to the none, right? If you keep dividing x's away, you end up with no x's, but you're left with that 1 that you understand is out there. It's another way to see why it's 1. And then finally, another way to see why it's 1, remind me, what's x squared times x cubed, for example?
6. X over 6.
X to the 5th, right? 2 x's, another 3 x's, 5 x's. Cool. Remember, there is no 2, there is no 3. There isn't a 2 or a 3 anywhere in there. There's 2 x's and 3 x's. What do I multiply by? What's the only thing that in our number system we can multiply by and it stays the same? 1. That's the multiplicative identity, right? If I multiply by 1, it stays the same. There's no other number that does that, correct? What is x squared times x to the 0? What do I do with the powers? Add them. What do you get? So x to the 0 must be 1 because I multiplied by it and the answer was the same as what it started with. You guys see that? That's another way to kind of, it's not really a full proof. It's pretty damn close. Do you guys, so there's multiple ways to see why something to the 0 power is 1. Okay, maybe. All right. And I think I'll do, yeah. Okay, so we got what they want from this? Okay, I'm gonna take this away. So can you guys come up with a way to investigate this? This is going a little further in the book, and I don't care. I want a complete idea of exponents for you. So there's a way to investigate this related to the way we investigated that. So think about it. Let me know if you think you know how to set up a problem that would help us figure out what that might be. Say again. That's what it is, but why? That's what I'm asking. Can you come up with a problem that would lead me to realize what that is? So what did we do for this? Did we do x squared over x squared? Because that would end up being 0, correct? Don't I now want some ratio that will end up being this? Then I can investigate it, right? What would have to be true? Let me put a 2 here. What's got to be down here so I end up with -1 at the end? 3. So we what? 2 minus 3 is -1? Okay. So that is a true statement, period, because we know I subtract powers when I divide like bases. We know that's the truth. Well, what's the other way to look at this? How many x's on top? 2, right? How many on the bottom? Holy shit. How many cancel? How many are left? Where? All right, there you go. So x to the -1 is 1 over x. A negative power just means flip. Okay, maybe. You guys remember that? It always confuses the hell out of students. And if you think about it, why does that make sense? How do I, if I have x to the 7th sitting here, what would I do to it to make it x to the 6th? I'd have to divide by something, correct? I gotta lose an x, so wouldn't I divide by x? That would make me end up with that, right? What's a more direct way? Couldn't I just take 1 away? And that would still be that? So this must be the same as this, because they both accomplish the same thing. I'm losing an x in both cases. If I divide by an x versus I have a -1 power, I'm going to lose an x either way. So they must be the same thing. I like it. Okay. And again, you're not going to see that yet in the book because officially we haven't gotten to negative numbers yet. Okay, I like it. We've talked about subtraction, but that is arguably different from negative numbers. Okay. Blah, blah, blah. Okay. Yeah, we talked about that. I like it. All right. Okay. So let's do this. Here, you guys try this problem out. Where is it in order operations, what we're talking about now? What was the order operations? OOP. Order of operations. The OOP. What was it? Tell me any way you remember. Order of operations. I'll get it started, please. Excuse, so parentheses exponents. Please excuse my dear Aunt Sally, or dumbass son, or division algebra skills, whatever you want to do. It's just a mnemonic device to memorize that, right? This is the, well, I'm not going to say that. That's freaking arrogant. But this is a better way to write it. I don't remember if I told you guys this, but you see this. I think I told you guys this. There are actual math teachers, and I've seen this firsthand, that will teach that multiplication comes before division. And I don't remember if I told you, but they just need to stop teaching, right? That's bad. And then you see all this, I did this before, I'm sorry. You see the Facebook things where, what is this? It's 16, it's 1. Ah! I'm like, oh God, what's happening? So why do I write it like this? Because that definitely comes first, no question. That definitely comes second, no question. Either one of those as they come, right? So for example, real quick, what is 4 times 4 divided by 4 times 4? This. I've got to vote for 16. You're not going to lose points by giving me a yeah. No? Okay. All right. Yes. 1. So I got to vote for 16. I got to vote for 1. Any other votes? I just want somebody to go, I think it's 3.9. Okay. All right. So let's work this out. Is there any operation that has dominance on another one? What's the only operations in there? Multiplication, division. They both have equal importance. I'm not going to do any of them first or any of them last. I do it as it comes. So the mistake a lot of students make is they do division last. Is division at the end of PEMDAS? Shit, no. So there's no reason it comes last. What's 4 times 4? 16. What's 16 divided by 4? 4. What's 4 times 4? 16. Okay. Real quick. What is the only number that is being divided? Just point to it. What's the only number that it says divided by this number? Divided by 4. Does everybody agree with me? It says divided by 4 in there. You can see it, right? So that would be the only number. If I rewrote this, it would be 4 times 4 divided by 4 times 4. The only number that should be on the bottom is that 4. Yes?
I think the parentheses are a little confusing though.
Understood. But what does that actually mean? This is beautiful. What does the parenthesis actually mean? It means inside the parentheses. What operation are they denoting here? Multiplication. I like it. But that's a good point. I agree. It can be confusing, yes.
One thing that could be confusing about it is that people like group the two and treat them like sets.
Totally. The most common mistake I see with order operations is students think division is last. Just always, no matter what. They'll just think division is last. And there's reasons why. If I do this problem here, what's going to be the last thing we do? Divide. But that is a very different problem from that one. Not just because it's got different numbers and such. Because do you guys understand there's understood parentheses? Anytime you write a problem with a big division bar, there's understood parentheses. Why don't we write them? Because we got eyeballs. I don't need them. I can see the long divisions bar, right? But if I try to put it in my calculator, I better put the freaking parentheses in, because thank God the calculators don't have eyeballs yet. All right, the TI 2000, I like to joke, and that's when Skynet happens and blah, blah, blah. Little calculator comes out, you Sarah Connor. Sorry. I like this idea though, because now you see, if you made that 16, how the hell did you make that 4 come down there? Do you guys see that? Okay. So there's only one thing that I should be dividing by. It's not fair to divide by 16 all of a sudden. Wait a minute, I was only divided by 4, right? Okay, maybe. Okay. So now, let's try something a little bit different. What if I had, what you got, Jeff, this here? 6 minus 3 minus 5 squared divided by 2, I like it. Very first thing is what? Inside the parentheses, right? 3 minus 5, kick ass. What's 3 minus 5? Negative 2. And one big mistake I see is students will make this become plus. What operation is that? If I do that, that makes a plus sign. What operation did I actually just do? Multiplication. But what, of course, comes before that? Exponents, right? And what is negative 2 squared? 4. I don't technically need the parentheses, but who cares? And then, of course, and from the very beginning, I try to point to students, you can tell what you're going to do last, correct? What's at the ass and the PEMDAS? Addition, subtraction. So I know I'm going to do that last. It's just going to come for the ride. It's 6 minus I don't know. 6 minus I don't know. So 6 is like, come on, guys. Okay, maybe. So then 6 minus 2 is 4. It's crazy. Okay. All right. Maybe. All right. So almost no matter what level of math I teach, I always get students who still have trouble with that kind of problem, which is a little sad. So I think I can't speak directly to what's happening in earlier math education, but there are certain things that don't seem to be understood as well. And I think it's because, and this is actually, teachers have to meet so many standards, and there's testing that happens. You have so little room to be creative and to explore ideas. And I'm not trying to make it sound like you shouldn't become teachers, you totally should. But I just wish there was more room. There was less standardized testing. There was less of this and just more room to just explore ideas with students. And I think because of that, for example, here's a really big example. What is it, if I want to do 20% of 13, what would I put into my calculator? Times. It used to be everybody straight out of high school knew what the hell of meant. Now, they're not sure. So few knows what of means, right? Okay. That's just one little example of, and I'm not really sure what that's connected to or why that's happening, but that is a complete thing I see. Over the last 15 years, the amount of people that know what of means has gone straight down. Okay. Also, the number of people that could do 7 times 8 has decreased, right? Okay. Let me see. Okay, good. There was nothing else there. No, okay, that was the last thing. So I want to do a little bit out of chapter 4. I'm going to show you a couple of videos. Then we're going to call it a day. I was considering, I want to show you something, just to show you. You guys remember these from a video we watched? Let me put it up on the overhead. I want to show you a couple things. So these little things where it can connect. Remember the one scene we watched where we got to watch the little kid just connect all of them together? And I don't blame them. They're very much like, gotta get this together. So that's good. Oh, okay. All right, you guys can see that. So you could do stuff like, can anyone tell me that by itself? Good. What other, I kind of like this kind of problem. What other type of problem could that be used to do with a student? So one way you could do this is 6 plus 5. Are these the same size? Yes, okay, good. What other kind of problem, and be as specific as you can. Yes?
You could do a subtraction problem.
Good. What approach would it be? Yes?
You could kind of like match them up and then see, oh, you have 1 extra on
So does anyone remember the name of the approach we're doing? So let me make it a little clearer. Green could be Gary and yellow could be Joseph, right? Gary and Joseph. And Gary's got 6 and Joseph's got 5. So what kind of a problem is that? What am I doing? I am comparing the two, right? Comparison is an approach, correct? So the comparison approach is where you have 2 different sets and then you just kind of, like you said, So you can tell a student, all right, Gary's got 6, and Gary's green. Okay, so they count out 6, and then you watch them put it together. Okay. All right, I'm gonna be a little kid. Put it together. Joseph, who puts it together, has 5. How many more does Gary have? And then they could do exactly what you said. Bam. Gary's got 1 more. Okay. I like it. Kick ass. How would you do takeaway approach? Sorry, that wasn't the answer. Takeaway would be very simple, right? So you can have the set method. This is a kind of an example of the set method. So you can simply just take 2 away and you can see what you got left, right? So I mean, there's so many, it's absolutely silly, the number of math problems you could do. What would this be an example of? Multiplication. I love it, right? And this is like a set method of multiplication. I got repeated groups. And then you can show them, okay, this would be 3 groups of 2. This is 3 times 2. Is everybody with me? How would you make it 2 times 3?
Rearrange it so that there's 3 in it.
Yeah, and then you can have the student realize, did you use all of the pieces you had? Did you have to take any more? No, so it's still the same result. Okay, I love it. So, if I were teaching elementary school, the very first time they ever touched these things, I would just let them do whatever the hell they wanted with them, right? Make a little house. And in fact, I think very often, I don't know if this happened here yet, but I gave these out at one point. At one point, we're going to get to play with these. You guys are going to, and I had somebody, I think this happened here. I don't remember, anyway, maybe not. Somebody constructed a little, something out of what I gave them, which is great, because then you're just getting used to these things and how they work and how they snap together, just getting used to the pieces. Then you can start throwing at them problems, right? You can slowly introduce kind of problems and just totally not even make connections between written mathematics. Just let them explore counting and putting things together and so forth. Okay, awesome. These are just fun to play with. All right. Just to let you know, there are manipulatives later that I really enjoy. I'll see if you guys agree, because I understand that a lot of us, who in here dislikes working with fractions much? Okay, a few guys. And then there's a few of you that probably agree and just don't want to raise your hand. There's some really cool manipulatives later this semester we're going to use a lot to model fractional problems that makes it more intuitive, and of course is more kinematic, right? So, have you guys learned about learning styles yet? Kinematic, auditory, a little bit. Okay, that's a huge topic. I might try to incorporate that in here. It's not really part of my curriculum, but there are tests you can take to figure out what learning style you have. So you're more aware of what learning style you have personally versus what your students have. Okay. So I want to do a little bit out of chapter 4, show you a couple of videos, and then we'll call it a day. Oh, I already had you here. That's good. You guys work together. Okay. So chapter 4. Again, just to remind you guys, it's going to be a lot of kind of wordy terminology, and they're going to reference very simple processes. There's one of the first things we talk about. So chapter 4 is all about mental math. So part of it's going to be estimation. Part of it's going to be related to stuff we've already done before, like 4 plus 7 plus 6. You would do the 4 plus 6 first. But it goes the next step. When I say estimation, what do you guys think of? Just to get a feel for what you've come in with. Estimation. Anybody ever been, well, this is no good nowadays. I was going to say, has anybody ever been a waiter or a waitress? But now, basically, every business has the tip calculated for people already, correct? Back in the day, they didn't. And then people could just stiff people and go, I'm not good at math. Sorry. And they leave, right? Anyway, sorry. Of course, I always say just pay the damn people what they deserve in the first place, so they don't have to live off the tips. But if I wanted to estimate how much tip to expect, that's a certain kind of problem. Because a standard tip, of course, is how much? Now it's 20%, so normally it was 15%. I've only tipped somebody 0 once, and I really did like a 0 because they were just evil. Anyway, sorry. Most waiters and waitresses I've ever had have been great people, and I want to tip them really well. So estimation, what I think of when I think of estimation, I think of rounding that comes into play. So if I had to do 78 times 7.9, what would you make that to make it quick to get a rough estimate? 78 times 7.9. 80 times 8. And then you know the answer is going to be a little bit more or less than it should be. So it was 78 times 7.9, and you made it 80 times 8. So the answer is going to be more than it should be. Does that make sense? Because I increased all the numbers, correct? Okay, so that's one topic in this section. We're going to fill in a couple things we haven't talked about yet. So for example, there's an interesting thing. Let me see what you guys think about this problem here. This kind of thing happens pretty often. How would you do that mentally? I want to see we go very slowly. Yes?
Is the distributed
Yeah,
numbers
yeah.
distributed?
In fact, there's a more direct way to do it. This statement right there, how many 21s are there? 17 21s. And what am I taking away? I'm taking away 13 21s. So how many 21s am I left with? 4 21s. But just to show you more of the work, in case you're not sure what the hell I'm talking about, what Ryan said is, what can I take out? 21. And what am I left with then? 17 minus 13, right? So I get 21 times 4, which is easy. But a more direct way is 17 21s minus 13 21s is 4 21s. I like it. Something else that happens a decent amount. What about this? Believe it or not, this is related. Yes?
Could you put the one variable underneath?
I could put that, sure. But I want to do it without like the non-result and stuff. How much of an 8 is this? Isn't this a whole 8? How much of an 8 is this? A third of an 8, correct? What's a whole thing minus a third of a thing? And you're all like, dude, you said fractions were later. Well, we can do this. What's a whole thing minus 1/3 of a thing? 2/3 of a thing, right? So 1 whole 8 minus a third of an 8 is 2/3 of an 8, which is 16/3. You guys see that? Okay. So that kind of idea, and again, this is sort of a distributive idea. If I take an 8 out, there's the 1 minus a third, right? You guys see that? So it is, again, the same kind of problem, just dealing with fractional numbers, not whole numbers. Okay. I like it. They also bring back some old hits, some stuff that we've seen before. What's a way I could do this? Bush, without doing long division and all that stuff. This is going to lead to something kind of interesting. What number below 168 does 3 go into really easily? 150. Do you guys see that? Isn't 150 divided by 3 pretty easy? So isn't this 150 plus 18? Now here's a really cool thing about division. Is division commutative? Is 4 divided by 2 the same thing as 2 divided by 4?
No.
Nope, right? 4 divided by 2 is 2, 2 divided by 4 is 1/2, totally not commutative. So addition, multiplication, commutative, subtraction, division, no. But what's interesting about division is, if it's on the right side, it will distribute. So you can do this. 150 divided by 3 plus 18 divided by 3. And it kind of makes some sense. So let me write this a different way just to really show you. So if I have 150 plus 18, what am I dividing by 3? Aren't I dividing the whole thing by 3? And then couldn't I just break these up? Now, if it was turned around, if it was 3 divided by 150 plus 18, that would be 3 over 150 plus 18, and I'm really hoping everybody understands you can't break that shit up. When the bottom is one thing, that is awesome for a division problem. When the bottom is one thing, I can split it up all day. Turn it around, I'm screwed, right? So that just becomes 50 plus 6. 56. All right. We've seen similar things with multiplication, where I can break them apart, do some distribution, and so forth. What we haven't directly said yet is division actually distributes also, but it must be right side distribution. I can't remember, this book calls it, I love it, right distributivity, just to make it really hard for me to say. Okay. So everybody with me on that? So there's two things happening there. Division distributes in a very specific way, and this is a way to kind of break the problem up into easier problems. Okay, so you don't have to do long division, for example. We've seen stuff, all right, here's something we've seen before. We just didn't give it a name. They're called compatible. Oh shit, how do you spell compatible? Is it an I? An A? Okay, thank you. Compatible numbers. Just showing off why I should be teaching math. We've done this before. So, for example, with addition, 4 and 6 are compatible numbers. 8 and 2 are compatible because they make a nice 10, right? So for addition, that's an example of compatible numbers. Give me an example for multiplication. There's quite a few. What are some compatible numbers for multiplication? Make 10 for me. 5 times 2. Make 100 for me. 25 times 4 is a good one, right? 50 times 2, all that kind of stuff, right? So again, how would this be used in a problem? If I saw, what do you got, Jeff? If I saw 25 times 27 times 4. I'm not going to do it as it comes, right? Why am I allowed to do it out of order? It's multiplication that is commutative. So I can do it whatever order I want to. You guys with me? So of course I'm going to do 25 times 4 first. 27 times 100, 2700. We've done that before, but we just didn't call them compatible numbers at the time. We've done one extra level on top of this before, and this is what's called compensation. So, for example, let me put this up here. Compensation. Additive compensation would be something like, what's a good example? Yeah. 38 plus 16. So when I say the word compensation, what do you guys think of? Anybody think of anything when I say compensation? What is money, right? And compensation would be money you get. So your employer takes some of their money and gives it to you. Do you see how that kind of correlates here? What do you wish was there instead of 38? You wish it was 40, correct? Does 16 have 2 it could let me borrow? Do you guys see that? So this guy gives some of itself to this guy. 40 plus 14, 54. So that's the idea of compensation. One piece gives part of itself to the other piece, so that it makes an easier problem in the end. I like it. So what about multiplicative? compensation. This would be something like 8 times 25 is a really simple example of this, right? What do you want 8 to give 25? The factor of. Multiply 25 by what is really nice? 4. Does 8 have a 4 it can give? Yes. So this would be, get out of there, 8. Take 4 away, it's 2 times 100, 200. Kick ass. So anytime one piece of the problem is giving something and giving it to the other piece, that's compensation, yeah.
Can you explain how you got to 100?
Yeah, I'm sorry. So the one step I'm skipping is I take 8 times 25. 8 is 2 times 4. So I take 4 away from the 8, leave 2, and I give it to the 25. Does that make sense?
Yeah.
Okay. I like it. What about, this is going to come up later, but I'm going to do this problem a little bit different way later. What about 78 times 5? Yes.
80 and 2.
Say again?
80 and 2.
Be really careful. I can't use subtraction or addition because the main thing is multiplication. I've used factors that'll work. What would you like to multiply 5 by to make a nice number? What's the best number to multiply by besides 1 or 0? 10. Do you guys agree with me? Multiplying by 10 is like, oh sweet, just slap a 0 on it. So what do I have to borrow from this to make this guy 10? 2. So if I take 2 away from him, what's left? Don't tell me 76. If I take a factor of 2, here's a cool way. All right, say it. 39, totally. So 78, isn't that like 2 below 80? Cut 80 in half, that's 40. Cut the 2 below in half, that's 1. 1 below 40 is 39. Okay, so if I take a factor of 2 away from him and give it to the 5, now that's an easy problem, right? Okay, maybe. Okay. I like watching your faces sometimes. Okay. And again, you can imagine this is going to have to be further along. I can't see. Here they're talking about this in grade 3, which does strike me as the right time to do this. By the time you're in grade 3, you've gotten a lot of practice with the basic operations. You totally understand how to count high enough, and you kind of know the multiplication tables of some very basic numbers. So then kind of extending it to playing with the numbers, playing with the parts of the problem to see how they can help each other out, then makes sense to be a natural next step. And one thing I'm really jealous about for any of you guys that are going to teach really young kids is they just want, just give me information, just give it to me. When they get a little older, it's like, right? And the young, they're just eating that shit up, right? So they want to play with this. They see this as another thing to play with, which is beautiful because that's what math really is. Okay. No. Good. Okay. Good. There's. Yeah. Okay. I want to show you a couple more things, then I'll show you the videos. Left to right. Addition. It's kind of weird. So before you teach carrying a 1 or carrying whatever and so forth, you just line them up. You can show a slightly different way. Where are you at, Jeff? There I am. So instead of lining these up and adding and carrying and all that kind of stuff, because at that point, they don't really get what that means. You could break this up, do 400 plus 200, so left to right. When you do it like this, where do I start? Right to left, yeah, exactly. So that's the right to left method. It involves a bunch of extra little stuff. If you do left to right, the first time I say that, you might think, well, that's never gonna work. What the hell are you doing? Yes?
You would have to group them into, like, you would do 400 plus 200, then 80 plus 50. and-
Yeah. 3 plus 8, right?
Yeah.
So you get 600 plus 130 plus 11. And each of these are relatively easy because they have a lot of zeros in them, or else they're single digits, right? And then I just have to combine those things. So you get 730 plus 11, 741. Okay. You guys with me? And then can you see what to point out here that would lead to the carrying the one idea? Does anyone see something you could point to and say, and kind of use it to connect to the carry one? Somebody else, sorry. You're fine. I love it.
Number 11.
What about it?
It's 1 over 10.
Yeah, 11 came from the single digits, but the one ended up messing with the tens place. I love it. You could say something very similar about the 130 messing with the hundreds place, right? So we're going to develop, for example, division is one we're going to spend a decent amount of time on. Several algorithms that all kind of lead to the main long division that we use. This is a beautiful little example of, before you even talk about carrying a one or whatever, this will lead a student in that direction naturally, right? Like, well, yeah, of course it's going to do that because that's what it would do. Okay. Remember? By the way, Thursday we have a quiz, and then I'm going to have a handout kind of reviewing all the stuff we're doing today that you guys are going to get to work on. Today is just my dump a lot of stuff on you day, right? And you're like, yeah, we get that. We're living it right now. Okay. Blah, 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 blah. Oh, what about left to right method multiplication? Sure. We'll start with something not too evil. 483 times 3. So instead of lining them up and doing a bunch of carrying and stuff, you would just, yeah, it's going to be the same idea, right? You're going to do 400 times 3 plus 80 times 3 plus 3 times 3. Do you guys see what's the hidden property I'm using to do this? What property am I really using? I'm not writing it in the way, but what's 43? Isn't 43 400 plus 80 plus 3? So if I take that and multiply by 3, I'm just distributing. I love it. And then you get 1200 plus 240 plus 9, so you get 1449. And again, you start to see the carry the 2 and all that kind of stuff kind of coming out. So a student did several of these kind of problems. You could start to point out where things kind of bleed over into the next column, right? Okay, I like it. So again, this is a beautiful example of a place that a parent would say, what the hell are you teaching my kid? Just tell him to carry the damn 2. And I don't know what it's going to be like for you. I really don't. Part of me is very happy about that. One reason I chose college is so I didn't have to mess with parents. I'm really sorry. But that's also kind of bad because I don't have some ally in the home who could actually help me keep an eye on the kid and make sure they're doing their homework, for example, right? Some parents will do that to an extreme, and some parents do it not at all. But anyway, you're going to figure that out. Damn it, Jeff. You talk too much and then you forget what you're about to say. I love it. Anyway, so this will be where you can start to develop the idea of carrying stuff in multiplication. There's something else I wanted to say and I forgot. It's too bad. Okay. Oh yeah, and do you guys, real quick, last thing, Ash, I promise, and then I'll show us some videos. I'll believe it when I see it. Check. Make a number that's a number. There you go. Everybody in here, do you guys know the quick way to multiply that by hand? Yeah, 41 times 2, 84. And then all you have to do is put the same number of zeros down, right? Because, and the reason that is 10 times 10 is 100, 2 zeros. And then if I just extend that idea, it's just multiplying so many 10s. So anytime I see this, it's a collection of 10s that have already been put together. So I just got to put them together with them, right? And to be really honest, behind the scenes are exponents, correct? Because 1,000 times 1,000 is actually 10 cubed times 10 cubed, which is 10 to the 6th power, right? And which is why you'll end up with 6 zeros. Okay, maybe. So the shortcut is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Bam, 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 bam. Dude. So I just want to make sure everybody knows how to do this. So let's watch a couple of videos of these crazy young people trying to